in this moment, size of the body is put into consideration, and we come across some terminologies which makes it more fun. Moments of forces are always taken about a point, always taken about a point or axis, and it is a rotational effect or twisting effect. So let me write the definition. Now, the moment of a force about a point or an axis is the turning effect of the force about that point, and it is equal to the product of the force and the perpendicular distance of its line of action from the point or axis. Perpendicular distance, product of the force and the perpendicular distance of the line of action from the point or axis. So, if you are to use vector representation, we will say it is the cross product of the force and the distance from the point or axis. It is the cross product of the force and the distance from the axis. And by work is the dot product of the force and the distance it moves through. So that is the thing. So you can now say it as this. So M, that is the moment, is cross product of force and distance. It's the cross product of the force and the distance. So let's look at it like this. If you have a force F and it is acting at a distance D, like this. If you look at it and this one, you can see that the angle is perpendicular. So M in this instance is equal to FD. M in this instance is equal to FD. Now let's now see if we have something like this and we have F like this. What are we going to say the moment is? We just make it like this. Can you see? And then let's call this place theta. You know, this place will be theta 2. And this place will be the perpendicular distance. You can see. So this place is the D. By the time you resolve this, you can see F goes like this. This is the perpendicular distance now. So it is going to be F times, and this place now is P. And what is P? P is D sine theta. D sine theta. So in this instance, M will be equal to F times D sine theta. You see? That's why we call it the cross product. That is how we express this. But to make it simpler, if we express this one, this distance, as in vector format, and this one in vector format, all you just do is M is equal to F cross D. And that will bring us to interesting aspects. Let's talk about the transmissibility of force and Varignon's theorem. Transmissibility of force. Stability of force and Varignon's theorem. If you have, decided to use vector notation, you won't bother yourself about this. But if you are still trying to do it in algebraic form, that's when you will consider this transmissibility of force and Varignon's theorem. I was talking about rigid bodies, and that is where you can talk about movement of forces. Please, when you are talking about rigid bodies, that's where we start talking about movement of forces. For particles, you can't really talk about movement of forces, and that's why I am always, trying to be aware of the term I'm using. Please. And I've explained what rigid bodies are initially. So now let's consider a rigid body now. A rigid body like this. And the force F is acting here. That's why it is acting. Let's say a particle. Out of all the particles in the rigid body is here. So, if this force is here, we now, on this rigid body, we now bring two forces, that is a force and another force, that the two of them are in equilibrium and they act along this line, this same line. So we have, but on another particle, like this and like this. If you look at it, this one and this one cancels. So the only thing that will have effect on this rigid body is still this F. I hope you are getting it. So let's say this is F, and this one is also F, and this one is minus F, and this one is F. Please, I deliberately use F throughout because they are equal in magnitude. For this one now, I have minus F and F. These two, the sum of this force will be 0. And they won't have any moment effect because they cancel each other. Now, let us now do something. This minus F plus this F. What happens? This one cancels and this one cancels. So this F remains. What are we trying to say? That if this, as this body is, and this force that is acting here, we bring it here on this line, it will have the same effect as if the force is acting here. But if it is not on this line, the effect will differ. So let me now state it in words. Now, so this is the principle of transmission of forces. If a set of forces act on a rigid body, the resultant of the set or the state of equilibrium is unchanged. If any force F of the set acting on the particle is replaced by F having the same magnitude and direction acting on a different particle, provided the line of action, that is the line of action, is unchanged, the force sets are still the same, equivalent. So I have explained before. So if one of the set force here is now placed here, but it's in the same line of action, it's the same thing. So if you have F1 here, F2 here, no matter what, let's say F3 here, and say F4 in this place. So, if at the end of the day, you move F4 away from this place, but you make it to now act in another place, but it's in the same line of action as F4, the resultant effect is still the same. Are you getting it? Because this F4 is not going to make any moment about this place. It's still the same thing. If you look at it, it's still the same thing. Now look at this. Varignon's theorem. This is R, and this is NON. Varignon's theorem. And it states that the moment of a force, let's call this F, about an axis is equal to the sum of the moments of its vector components about the same axis. Before we go on, please, I would like to reiterate that when we have anticlockwise moments, we have positive. When we have clockwise, we call that one negative. So, what I am not trying to say is this. If we have a force like this, we can break it into components. We can break this distance, D, into components. And then, we just do the multiplication of each force and the corresponding perpendicular distance and get our total moment. Look at this now. If I want to break, let's say this is D, this is theta. The moment will actually be this. Let's call this one P. Let's call this P. See. So this will be the moment. M will be equal to L times P. But we want to look at it from a certain perspective. This one, you can see. Let's call this dx. And let's call this dy. Let's call that one dy. Here. Now let's look at the diagram. This is the perpendicular distance to the line of action of F. I designated that as P. For this place is D. And we've gotten P area. Let me use small letter here. This one too is small letter. Now, if you look at the distance AF is equal to P and is equal to AC plus CF. Let's establish that this one and this one, and this place is perpendicular here, and this one too is perpendicular here. You can see. Now, let's look at something. This place is theta. That is the angle of the line of action of force. This place will be theta. Vertically opposite angles are equal. Now, if this place goes like this place, if you draw it straight down like this place will be like this. And this place, okay, sorry, I don't even need this. This place is perpendicular here already. So which means that this place will be 90 minus theta. And this place too will be 90 minus theta. Vertically opposite angles. Since this is a right angle triangle, this place will be theta. So we have established that to be theta. Now, you know this is AC. This is perpendicular to this one from here. So AC, AB, and BC, they are right angle triangles. So AC is equal to AB, look at it, AB sine theta. Sine theta. We have gotten that one. This place, AB sine theta. Now, let's also look at this place. This place. If you look at it, CF will still be equal to BE. Look at it here. CF will be equal to BE. And if you look at this place, it's perpendicular here. And this place is facing this one now. That is the component of D along X direction. And this is component of D along Y direction. This is dx and dy. Can you see? So this place now, what is it going to give me? It is component of D along the horizontal direction, sine, because this one is facing this place now. Is it sine? Okay. This place. So BE will be equal to AC now. Let's find AC. From this, I go to this angle. And, okay, let me start again. Now, look at this. Let's look at the moments of F about A. F acts like this. Okay, let's make it act downward. F. So F acts downward. So if F acts downward, its moment about A will be the perpendicular distance of its line of action from A, and this is it. So F is F times, let's call this place P. Now let us break this direction, this D, into two perpendicular components. This will be dx and this will be dy. We have that already now. So let this one continue like this. Let's now bring this one down to touch this place. And you know from our geometry, this angle here will be equal to this angle here. Now, I've been able to get AB to be AD cos theta. Now, for me to get BC, BC is equal to DE. If I project it like this one is parallel to this one and this one being equal. And if you look at it, this is DG. And DG is now the hypotenuse, and DE is now the opposite. So DE is equal to DG sine theta. And if you look at DG sine theta, DE is also equal to DC. Have you gotten it now? DE is also equal to DC. Therefore, N is equal to F times P, which is equal to F into AB plus BC. N will be equal to F into, and please, DG is equal to DX. DX sine theta, because DG is equal to DX. See. So it's going to be AD cos theta plus BC DG sine theta, which will give me F into dx. Here it is. Dx sine theta plus dy cos theta. You can see dy cos theta. Dy cos theta. So if I should break this down, I'm going to have n to be equal to f cos f sine theta into dx plus f cos theta into dy. So you can see, which means that if you break f into its components, the moment of its component about this place, the sum of the moments, is going to give us the moment of f. So the moment of f about A. So it's very simple. Just like when you break it into, I said it, into its vector components. Express this one in its vector form and D in its vector form. Do cross multiplication, cross products, you get your n. So, and if you don't want to do that, just break this one. So this one times dy, so which will give us fy times dx, because that is f sine theta, plus fx dy. So that is the simplest thing I want. The simplest way you can express it. Fy times dx plus fx times dy. That's all. Just consider the direction. If it is positive or if it is negative, know how to add it, and that is all. Now, that takes us to another thing. So, what are we trying to say now? That for rigid bodies now, we have additional condition now. At equilibrium, summation n will be equal to 0. Summation f will be equal to 0. That is for rigid bodies at equilibrium. But if it is just for a particle, for particles, we don't talk about moments. All we talk about is summation f in any direction will be 0. That's what we talk about in particles. So we have got to the additional condition for rigid bodies to be at equilibrium. Now let's talk about the effect of forces on rigid bodies now. We've talked about the effect of sets of forces on particles, on rigid bodies. So, if two forces act on a rigid body, they must either be parallel, just like we said the other time, or they must be concurrent. Just like the body. They will either be parallel or concurrent. So, if they are parallel, let's talk about if they are parallel. If they are parallel, if they act at the same points, the sum of the forces acts at the same points. The sum of the forces will just be algebraic sum. Sum of the forces will be algebraic sum and acts at the same points. I'm talking about the resultants. So the resultant will act at the same points, and the moments generated will still be, it can generate moments and it might not generate moments. So moments can be generated or not if the forces act in opposite direction and equal. So what I mean is this: if a force acts like this and another one acts like this, that is, they are unlike. If F1 is equal to F2, there won't be any moment generated. So that is just summary of this thing. So I now take them one by one for parallel forces. I will take that of the ones acting like parallel forces and unlike parallel forces. So now this is just the summary. So now let's start talking about each. Now we have two like parallel forces. Let's say F1, F2, A, B, C. So what are you going to do? The sum, this is R. Since they are parallel, R will be equal to F1 plus F2. You sum it algebraically, but it's going to act in the middle of the two, and we will see it as acting in a region within A and B, and we see it as the center of the action of this sum of these two forces. How do we get C? The moment of R about C will be 0. So summation N about C is equal to 0. So now we have to get it like this: F1 times AC will be equal to F2 times B times CB. Let's put it that way. If you look at this, the moment will be 0 above C. So this one is clockwise, this one is anti-clockwise. So what do we have now? F1 over F2 will be equal to CB over AC, which means that the distance will be inversely proportional to the forces. So if F1 is higher, it means AC will be smaller than CB. You understand? So that's just a simple way of getting the point at which they will act. If I have told you before that if it's at the same point and it's at equilibrium, the two of them are equal. Now let's look at when it is unlike, two unlike parallel forces on the body. What are you going to have here? Let's say it is like this. You are going to have force F1, force F2, and let's make this one A and B. It's going to the resultant is going to be either after this place or this place. It's going to be before A or after B, depending on the sizes of these forces. Depending on the sizes of these forces. So R is going to be, if this let's say F1 is greater than F2, it's going to be, if F2 is greater than F1, F2 minus F1. That's what it's going to be. Now, it now means that the resultant will act beyond F here. That is where R will act. R will act after of this one about this place must be equal. If it comes beyond this place, it's going to always be, this one is always going to be bigger. So let's find what point R will now be C. So which is that F1 times AC is equal to F2 times BC. Please, this is for unlike forces. And F1 is smaller than F2. So F1 over F2 is equal to BC over AC. And you have said that R is equal to F1, F2 minus F1. So that is it. So in this case, F1 is smaller and BC is smaller. F2 is bigger and AC is bigger. So just understand this and then you solve the problems under this. Another point of interest is when F1 and F2 of unlike forces acting on a body are equal. Let's look at this. F1, F2. So, by the time you look at it, F1 is equal to F2. Therefore, R will be equal to F1 minus F2, which equals to 0. But we are going to have a timing effect because the moment of this one is bigger than the moment of this one. And sometimes it might just be from here to here even. You can even have it like this. So we are going to have something we call couple. This combination gives us what we call couple. When two unlike forces, two equal unlike forces act on the body, two equal unlike forces. So we have what we call couple. So we have moments, but we don't have force. So that combination is called couple. And couple is torque. So N in this instance is going to be Fg. That is the distance between the two forces. The same thing here. So N in this instance is equal to Fd. That is for couple. Now let's talk about when the forces are not parallel. Unparallel. So we are going to have resultants by our normal triangle parallelogram or any style. So R is going to be like this, summation F. And we can know where R acts by getting a point on the body. On the body. Where total moment is equal to 0. If it is in equilibrium or where the force R, that resultant, will give same moment as the total moment of the two forces acting on the body. Now for three forces, it will just be like two forces extended. That's all. If they are parallel, you add them and you take moments. You add forces, add moments. And for analysis purpose, especially when in equilibrium, summation f will be equal to 0, summation n will be equal to 0 in all directions if in equilibrium. And another thing I want you to know that if the forces are in equilibrium, they must pass through a point. They must be concurrent. If the body is in equilibrium, the forces must be concurrent, because there won't be any moment. It will be in equilibrium. So that helps us in analysis a lot. That helps us in analysis a lot. So all the things we have said about 3 or 4 forces or more forces on particle applies in this case. And moments is just the only difference. So I will now add, okay, so all conditions, you just view the forces as if they are acting on particles when you are handling them on a rigid body. The only thing you now need to just consider again separately is the moments. Let's talk about it. So we know that for a body in equilibrium, summation m equals 0. That is clockwise moment is equal to anticlockwise moment. That is the key. So this now takes us to a point on the body, just like I treated in moments. As in, there is a point where the total force, that all the forces seem to act through. Points where the weight. So in this instance, I want to talk about the weight. Where the weight seems to concentrate or pass through in a body is referred to as center of gravity. So in the same way, the point at which the mass seems to concentrate or pass through, irrespective of the position of the body, will be referred to as center of mass. So here, irrespective of the position of the body. So when you want to get this center of gravity or center of mass or whatever, there are techniques we use, but most times you just place it on a pointed, you just place the body on pointed objects. So if it balances, that will be the center of gravity. That will be the center of gravity. So this is also used in analyzing forces acting on an object, because we see this as intrinsic force already embedded in the object. So you need to know about center of gravity as well. Now let's talk about stability of objects slightly. What I will say when we are talking about stability of objects, it is that when an object is in a position, how far will it go away from its initial position if a force acts on it? Let's look at a body like this. If a force acts on it, it will bend a bit and come back to its position. It will bend a bit and come back to its position. This one is referred to as stable. You know, it's about the body remaining in equilibrium. Now let's look at if we have a body like this. Any slight touch, it will just fall down. Any slight touch, it will fall down. This is unstable. That is, when slight force acts on it, it moves away from its position of equilibrium. It moves away from its position of equilibrium. Now let's look at this one. You see, once you push it, back. No matter how you turn, it just take a new position. That's all. That's why it is called neutral. And if you look at it, it is all related to its center of gravity. It's all related to the center of gravity. About displacement of the center of gravity. Look at this one. The center of gravity is here now. If it is tilted, the center of gravity is still within the point out away from the point that has like a fulcrum. What do I mean? Look at this one. So look at this. For the stable, CG. Now, if a force acts on it, you see, the center of gravity is still like this. It's still out of this point that acts as the fulcrum. So it has tendency of coming back here conveniently. So that is why it is stable. But for this one, any slight push to this side, you see that the center of gravity will be on the same side of the force. See. So automatically it will just fall down because of the push or pull. So CG here now. So if you look at it, there is no moment that balances this force. It just goes away like that. So that is why they test the stability of our cars, machines, and whatever. This helps us for the stability of cars. But when you look at two-wheeled vehicles like motorcycle and bicycle, you will need to use something to balance them because they are non-stable. They are unstable. Now let's treat work, energy, and power. What is work? Work is the product of force and distance in the direction of the force. In the direction of the force. Now, but if the force is at an angle to the direction, let's say the force is like this and the distance moved is along this direction. So this is the direction of the force and distance. So this one will now be, in this instance, W is equal to F cos theta times T. So that is the component of the force along the direction of the distance. This shows that work is scalar products, dot products of force and distance. If it is, expressed in vectorial form, while, moment is vector products of force times the distance at which the force is applied. So you can see the difference now. Let's go to energy. Energy is the ability to do work. So in this instance, we have several forms of energy. You can talk about mechanical, electrical, chemical, heat. Even you can talk about radioactive or atomic energy, etc. So the basic form of energy that we always work on is mechanical. And most of this, we measure them based on the mechanical energy they can bring out. We equate them to the mechanical energy. And why? Because it's the basic form. And we always have it. It can be easily connected to this formula of work, force times distance. Hence, let's talk about the mechanical energy. When we talk about mechanical energy, the basic forms are potential and kinetic. Potential is energy. Potential energy is energy possessed by virtue of position. Possessed by virtue of position. So in this instance, you can easily talk about work equals force times distance. We talk about it when we are talking about the gravitational field, or in springs, or in extension of something like elastic bodies, because it is about the position. Force is being worked against. Let's talk about that of the gravity, which is the most common one. Potential energy. Okay, gravitational potential energy. Potential energy. You know, in this instance, a body of weight, because under this condition, this force is not changing. It's moved through a distance h. At this height, it has worked, the force W has been worked on to move to h, which means that in this place, work done will be equal to WH. And W, weight, is equal to mass times gravitational intensity, or acceleration due to gravity, mgh. So, what happens here is this. The work done here is equal to the potential energy. For spring, or any other situation, the formula to get the potential energy is different from this, because when you are talking about spring, the force varies, because as you are drawing it, the force is increasing. I'm limiting this to gravitational potential energy. So the work done here is the potential energy in this instance, because it's by height of its position, by virtue of its position, which is the height, that is mgh. So it's a common form of calculating the work done, or the potential energy, when work is done against height. Now, we are now going to talk about kinetic energy. Kinetic energy now. Okay. In this instance, it is by virtue of motion. Energy possessed by virtue of motion. And work is equal to F times distance. That is work. Let's now talk about if a body of mass M is acted upon by force F, it means that it is going to have acceleration A, which is equal to mA times d. That is, if a body is moving with, it's being moved by force F over distance d. So this is the work done. But you know that when a body is moving with acceleration, the velocity will be changing. The velocity will be changing. So, and if a body has an acceleration of A over a distance of d, let's think of what the velocity will be like. Let's go to our equation of motion. We know that v squared minus u squared, v squared equals u squared plus 2ab. You can see. Therefore, v squared minus u squared over 2 is equal to ad. Let us now take it like the body moves from the body started from zero position, from zero velocity, from stationary position. Therefore, you can now say v squared over 2 is equal to 8. Let us now substitute this in this equation. So we are going to have m equals v squared over 2, which is normally mv squared. So by virtue of the position of motion, that is mv squared. And we always talk about this when the body is moving with constant velocity, or the body starts from zero. When the body is moving with initial velocity u, and later, due to force applied on it, its velocity increased to v. So let's say u is initial velocity, v is final. If a force F is acting upon it over certain distance, you can easily relate the two by saying Fg will be equal to half m v square minus u square. So you can see this is applicable easily if initial velocity is 0. But what you are saying is, when you see a body moving with this velocity, at that point the kinetic energy is half mv squared. So with this you can maneuver yourself through so many situations. Like me, I like working with energy work than other aspects because this one is scalar. Once you can gather all your indices, you can easily work your way out. Now when you are using force and other vector quantities, you have to consider direction and so many other things. Let's talk about power. Power is the rate of doing work. So if you can just relate it like this, P equals to W over T. That is all. The work done over a certain time divided by the time used to do the work. That is all about power. So if assuming you have something like a body moving with constant velocity, you can easily say P equals to F d over T. F. And sometimes F might vary. And you know what your D is. So you can easily get it like that. Maybe using integral calculus and whatever. So it's very easy. Or differentiation. Now let's talk about conservation of energy. We know that in a closed system, and what do we mean by closed system? A place where no force is being allowed to come in or to go out. No work is done on it. Energy is neither. Energy can neither, let me put it like that, be created nor destroyed, but can be converted from one form to another. Now let's talk about a body moves from the ground level to height h. The work done here is WH. Let's call that one PE. If it comes down, no hindrance, nothing, what happens? It will be converted to kinetic energy. That work that took it up, come down, is now converted to KE. E is equal to half mv squared. In this instance, we call this closed system because either way you look at it, the energy at this point, nothing is lost. It did not work against any force that drained the energy or converted the energy to some other parts along the way. But let's look at, and we call this gravitational force because that is what created the W. Gravitational force. We call it conservative force. And gravitational field conservative field. But let's assume you put a book on a rough table. If you move this book here, you work against frictional force. Frictional force. As you go, you work against frictional force. As you come back again, you work against frictional force. You will realize that at the end of the day, the energy will not be the same as the total that went forward and the total that come backward. In this instance, energy is used upward, energy is released downward. So it retains that close conservation. But in this instance, energy is lost to the frictional force. So you cannot say, oh, the energy I used to the front, by the time I come back, it will drop, it will be retained. I can use it backward. No. Therefore, like this one, or air resistance, like when a body is falling, you throw a body and there's serious breeze, you'll see that it will reduce the efficiency of the energy you are applying. So in this instance, we say it is non-conservative force and non-conservative field. So now let's talk about the unit of work and power. The unit of work is the same thing as the unit of energy, and it is called joules. Joules. It is the work done in moving a force of 1 Newton over a distance of 1 meter. Please note the units of each, because you can have bigger units and smaller units. You can have centimeter, decimeter, millimeter. So it's the same way you can have it in Newton. That's why we stress the unit. So 1 joule is equal to 1 Newton times 1 meter. You can have bigger quantity. You can have something like kilojoules, and we talk mainly about kilojoules. You can have it in megajoules and whatever. So it depends. And this one is 10 raised to the power 3 joules. Now let's talk about the unit of power. Unit of power is always referred to as watts. Please, I am talking about SI units. SI units. SI units. So, and it is the work done per second. That is 1 joule in 1 second. 1 joule per second. So, what is 1 joule per second? We can have higher values for watts. We can have kilowatts. That is 1,000 watts. That is 1,000 joules per second.